So, welcome to this week's VLSI Insider. This is Dan Hutchison.
This is Andrea Lati.
This is Jason Apt.
And this is Risto Puhakka.
So, there's not a lot going on these days in the last week or two, other than, I know, Risto, you just did a new 2020 forecast and it was a big yawn.
Yeah, it was basically 21 was basically known about 40% increase on the equipment. WFE is going to be north of 90 billion this year, so it's a huge numbers in multiple levels. The interesting thing really is what came out of the critical subsystems side. The forecast is about 30% growth for the year and equipment on 40%. So that kind of confirms one way also the 10% price increase or ASP increase going in the equipment side where the subsystems are in the long-term supply contracts with more fixed pricing. So that's kind of an interesting and it kind of confirms what we already know and have been seeing indicators, but that's just one more data point to confirm that. So that's the thing. But then Andrea, as soon as I release a forecast, Andrea starts to tinker around it. So what about the 22, Andrea? You got that already going?
Yeah, we just had a monthly update, and there were no changes to the 2021 forecast. They were the same as what we had in August. However, we did upgrade the forecast for equipment for 2022 from 6.5% to about 10.5%, so basically double digits. And the reason was that we're seeing a lot of activity in the equipment space. There is a lot of unfulfilled demand that is rolling in 2022, and the orders are just too strong at this point. So I think a lot of that will roll into next year. And that was the reason for going in double-digit growth. It could even be higher than that, but at this point, we're basically moving in that double-digit territory.
So everybody's concerned about all this spending. And Andrea, when you look at it in terms of the capacity that's planned to be put in place, but it's unrealized yet, it's not actually making wafers in the next year or two, how much does that account for, would add capacity to today's production capacity, which is maxed out?
I'm not going to go about talking about MSI here, but it's not a significant jump there. And part of that is because there is some inflationary pressure that, like Risto mentioned, that at least 10% is real price increase. So it's not really a physical increase in the fab in terms of output. There are conversions that are happening and some capacity that's being added, but I believe if we look at the overall capacity increase for this year, it's only about 11%, which is not a big number actually, considering that there wasn't much done the year before and the previous year, right?
Right.
So, and the industry has been growing quite a bit.
Right.
And so they need to start catching up actually. And if you look at it from that perspective, actually, we are not seeing any huge increases in capacity. And most of this, increase that we've seen at the production level is because, companies are running very, very high utilization rates, and whatever capacity that comes online gets converted quickly and then run at very high utilization rates. So, but it is really driven through, getting the most out of, the existing fabs.
Okay. But, I remember seeing in your TCI graphics yesterday that you had an unrealized capacity at about 15% of capacity. Yeah. So.
Yeah, but that's spread out. It doesn't, even next year, it's going to be probably rolling throughout the year. It won't all come in January, right? Because there's always this lag.
So Risto, what about this 206 billion that Samsung's talking about? How does that square with just his 15%?
The chip makers have been giving out these big numbers, 206 billion or 300 billion, and then they give some time frame, 3 years, 5 years, 10 years, and you really need to look at that relative to their historical spending, and you need to really look at what's on that number, that 206 billion, and basically, Andrea, you did the math on that. But
so basically it was 206 that they are planning this next year versus 185 that they did in the previous period. So the increase is only 14% if you look at the aggregate level.
So it's just not out of line at all, is it?
No, it's not.
No, and it's just a, but it also the message on those, it's a PR message. Hey, we will have capacity, we will build more. As a customer, don't you worry, we will have it.
Yeah. Okay.
So that's kind of the messaging out there, and it's kind of important not to take that number out of the context and look at it within the stream of data, and that's why it's important to look at that way also.
Sounds good. So Risto, I really want to know what TSMC's gift to the industry is. You keep talking about that. What the
heck are you
talking about?
Oh my God! As a business guy, it's a tremendous gift. It's basically, if TSMC announced, and I like to take the higher number, 20% price increase, to be implemented. That's a gift for the whole industry, because now everybody can go with the 19% price increase and tell their customers, aren't you lucky you didn't get 20% price increase? But in a sense, it's a recognition that we're gonna have a basically higher cost, higher expenses, basically inflation working through the whole supply chain in the industry. And then of course there's somebody who's going to have to figure it out, whether it's the consumer electronics supplier or Apple is this world, how the device pricing at the end of the day will go, and that will define it in how it works in the end markets. But in the general thing, I like to joke, it's a tremendous gift by TSMC to the industry.
You think it could be a major inflection point, like we saw in autos in the 20s, where all of a sudden we just went from prices always going down to prices incrementally following inflation?
Huge possibility for that, because it's basically the expectation through the industry is that the prices should decline 2 to 3% per year because of Moore's law and efficiencies and everything else. And we already know and have seen it. It's not holding all places up, and now it's like, okay, is this going to work through all of it? All types of devices. It's going to be really interesting and see if that has an opportunity to become an inflection point.
So I want to turn to Jason now, because when we start to look at what's going to drive all this growth, right? A lot of it, what we're seeing is more and more AI, but the AI needs sensors. And you've been seeing some really interesting things happening on the sensor side of the world.
Yeah, absolutely. I mean, image sensors are one of the most interesting parts of our industry, at least to me. I mean, so many different applications. And what I've been looking at over the last probably few weeks or so are sort of non-traditional image sensors. They're called dynamic image sensors, or maybe more accurately, dynamic vision sensors. So if you think about a normal image sensor like you'd have in your phone, it is still sort of based on capturing a frame. Kind of imagine a shutter coming down and capturing a still image. The difference with a dynamic vision sensor is that it isn't capturing a frame. In fact, what it's doing is every pixel is always on the lookout for a change, probably a change in brightness. And it can do this really, really fast because you're not trying to capture an entire frame, whether it's 60 times a second or 100 times a second. All you're doing is you're looking for changes in individual pixels. You can get speeds 10 times or more faster. It also has a far better dynamic range. For those of you sort of with a math bent, it's actually logarithmic detection rather than a linear one. And so when you combine those two pieces together for industrial applications where high speed is important, dynamic range is important, it's pretty clear. All kinds of industrial applications, and you think about the automotive market, where in fact the whole reason of having these sensors around is to look at fast moving objects relatively and detect very small variations so that it can head back to the processor to figure out, is this important, is this not? And so these sensors are really interesting, but there's a downside. The pixels themselves, or if you include the peripheral circuitry, are huge. 10 microns by 10 microns versus maybe what you'd see out of Samsung. We're getting closer to the half micron by half micron size for like a single frame, a normal image sensor. And it's because it's so complex. Now, one of the ways that the industry is moving, and we can actually take advantage of other technologies, you think about hybrid bonding. And so there are a number of companies right now that are looking at using hybrid bonding techniques, so very high density, you can get wafer on wafer, to ideally actually get to a single pixel, and you're actually pumping right out to your processor, which is sitting on the back side. So you get the density improvement, you get incredibly high bandwidth, high speed, right to your processor. So again, we're talking about hybrid bonding at AMD, as we talked about a couple of weeks ago, massive amounts of cache against the processor, but there's so many more applications in the hybrid bonding space, including things like this dynamic vision sensor. The hybrid bonding, the 3D packaging, more and more important in our industry.
Yeah, the hybrid bonding is coming up on different applications. There is actually a lot more than meets the eye right now. In just which I don't want to say conventional packaging, but the natural thinking is, hey, this is going to be great in your packaging. But we see it on NAND manufacturing. Now you're bringing the vision sensor technologies, and probably we're just kind of scratching the application space on that with even those.
I think that the interesting thing that's coming too along that same line is that, we've been talking about hybrid, heterogeneous stuff for 20, 30 years now. But now today what's happening is the test technologies come along and the design technologies come along, where before the design technology really couldn't design a chip that was broken up into multiple subcomponents. And so if you can't design it, you can't make it.
Absolutely.
Those barriers are broken now, and you can do a lot.
You can. And I mean, the complexity, like you said, actually increases, right? You think about trying to pump your image data to a processor, not on the same chip, but actually to a different chip through the hybrid bonding. I mean, now that we have the manufacturing technology, fantastic, but you still need to be able to design the architecture, basically, to be able to accommodate that.
Yeah,
and that, of course,
the signal path becomes really complex, and it takes a lot longer, a lot more energy to get it out of the chip to the other chip. So now you start looking at things like, because in the old days they were just using wire bonding, right? And that's a really power hungry way to move data around.
Yeah,
absolutely. So now you can do so much with through hole via and all that stuff, and plus you can test die to the point where they're as good as if they were in a package. So it's a really exciting time going forward.
Gotta love this industry.
Okay, so thanks everyone for taking the time. I appreciate it.
Thank you, Dan.
Thank you, Dan.
Thank you, Dan.